We're back on section 10.2. This is a follow-up to the last section where we're talking about having two samples instead of one sample. And if you remember last time, we talked about two samples where those samples were before and after tests. Now we're talking about two samples where they're independent. So the big idea here is that our samples are independent of each other, and that means that one sample should not impact the other. So some of the examples that I mentioned last time. So some of the examples I mentioned last time is your test. So what you score on your test shouldn't influence what someone in a different group would score on their test. If you're doing medication, whether one group of people gets well or not shouldn't affect whether the other group of people get well or not. So things where the two groups should be disconnected enough that whatever happens in one group doesn't influence the other group. Okay, so these are two independent samples. We're going to create formulas, and we're going to have a lot of formulas. They're going to be a little complicated. But what I really hope that you see is that the formulas aren't as complicated as they appear. There's really only two big differences, and that is instead of having one sample where we have one x bar, we're now going to switch to having two x bars. And so we'll have an x bar 1 and an x bar 2. So instead of having one average, we have two averages, and we subtract them because we're looking at the difference between the two averages. Because we always want to ask the question, we have these two samples, are the samples the same or are they different? And the way we do that is by subtracting them. The other big thing that we'll see is in the past we always had a standard deviation, and we would take that standard deviation and divide it by square root of n. And that's the way that we dealt with the standard deviation for our sample. Now when we have two samples, it's going to be a little bit messier, but it's going to look like this. We're going to have the first standard deviation squared over n1 and the second standard deviation squared over n2. Now, this looks a lot messier, but if you close your eyes and pay attention, you'll see that it actually makes sense that this would be the right formula. So what if you had only one sample? Then you'll notice that you'd have the square root of sigma squared over n squared. Well, the square root of the squared gives you just a plain sigma. So if you covered up one of the samples, you would get the same formula. So the way you expand from one standard deviation of one sample to two samples is you put it all under the square root, square both your sigmas, and divide by your n's. So when we go through our formulas, all we're going to do is we're just going to replace our averages with the difference between two averages and replace our standard deviations with this new standard deviation formula. So I hope you see how they're familiar and they're just like small variations of what we used to have. Okay, we're going to start with how to do a hypothesis test. And first, let me apologize that I did not come close to giving you near enough space on this piece of paper. So it might really be a good idea for you to go grab a separate piece of paper to write things down on, because you just don't have near enough space to do this. Okay, but here's our hypothesis test. This is our old hypothesis test. So this is what we did in the past whenever we did a hypothesis test. We would let mu equal to a number. H naught would be mu equals some number, and H1 would be mu is not a number. Well, now we're going to look at our new version. And now what's our null hypothesis going to be? Well, we have two averages instead of just having one average. Instead of just having one average, we have two averages. And so our null hypothesis, well, if there's nothing going on, if you're studying an effect of a medication, the medication isn't working, it's not doing anything. You're studying the effects of a teaching method, and the teaching method isn't going to work. What would you expect? You'd expect the two groups to have the same average. So our H naught is going to be that the two averages are the same. And our alternative hypothesis is going to be that one average is either greater than, less than, or not equal to the second average. So this is going to be our hypotheses. Notice they're almost the exact same, except we're saying the two averages are the same and they're not equal to. Okay. Now, what's our new test statistic going to be? Well, instead of having our old test statistic, which was x bar minus mu divided by sigma over square root of n, we're going to have two x's. We're going to have x1 bar minus x2 bar, And then instead of having 1 mu, we're going to have a mu1 minus mu2. I'm writing that kind of over at the side, and that's okay. We'll see why in just a second. Divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. I hope you can read this. It is in the textbook if you need to look it up. And this is actually the same piece that I wrote just a moment ago. So our standard deviation changed to this new kind of fancier version of standard deviation. Instead of having 1 average, we now have 2 averages, and we subtract them. Now there's one thing we need to think about. What is mu1 minus mu2? Well, mu1 minus mu2, notice that these are always equal. So what does that mean about this? That means this is always going to be 0. So if they're equal, mu1 minus mu2 is always going to be equal. So we can actually just erase that from our hypothesis altogether. And what we get is we get our new formula, which is x1 bar minus x2 bar divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So this is our formula. Now, to find our p-value, we find our p-value the exact same as we did over here. So once we have a z, we do this the same, and then we come to our conclusions just the same. So really the test is almost identical to what we've done before. The only difference is we've changed our formula just a little bit to make it messier, and we've changed our hypotheses ever so slightly. Okay, so let's come over and let's tackle this exercise 10.2. Let's tackle that first question on exercise 10.2. I'm going to call it A, even though I didn't put an A and a B, we'll just call it A. Okay. So test the hypothesis that the second chemical has a greater reaction time than the first chemical. So what we always do is write our hypotheses down. Our first hypothesis is that they're equal to each other. And by the way, this is free points on any sort of test or quiz. You know, that the two hypotheses are equal is always the case. And then our second one, we're testing the hypothesis that the second chemical has a greater reaction time. So that means we need to write our equal sign like that mu1 is less than mu2, because the second one is going to have a greater reaction time. Okay, now what we're ready for next is to write down our test statistic. And our test statistic is going to be from that formula we used just a second ago, and that is the z equals x1 bar minus x2 bar divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. I should make that square root go all the way down so it looks a little prettier. Okay, this is really messy, but it's not that bad, because when you read the problem, you'll see the problem tells us everything. And in fact, most of them are even labeled. So x1 bar was 16. x2 bar, I really messed up writing down x2 bar. x1 bar was 16, and it looks like x2 bar was 21. And then we put our big square root on the bottom. It looks like the first standard deviation was 1.5, and we square that and divide that by the first n. So that's how many times we reacted the first chemical. And it says we reacted the first chemical 13 times. So we had 13 reactions. And then plus, a lot of people put a minus here, but it's not a minus, it's a plus. And then we've got 4.8. Well, let's see, the second one was 4.8 squared, and then divided by 7. So just, I said a lot of people put, it's a mistake that students make. They often will use a plus here instead of a minus. It makes sense because you're subtracting, that you'd be tempted to also subtract. But think about this. Standard deviations, when you combine them together, they don't cancel out. They don't subtract. Because if you have a little bit of standard deviation, it's a little bit of variability, and then you add another collection of a sample, and you've added more variability. So the variabilities became larger. So we always add them. Okay, put all this in your calculator. It's a bit of a mess to put in your calculator, but I wish you the best of luck. Be careful. What I see students doing frequently is typing 16 minus 21 divided by, and then they'll type the square root. Well, if you don't tell your calculator to put parentheses around the 16 and the 21, you're only going to divide 21 by the square root. You're not going to divide the entire top by the square root. So it's real easy to get your parentheses off and have the order of operations mess you up. So put parentheses around that on the top, and then the square root, make sure to include everything on the bottom as it's written. Okay, but if you put all this in, if I did it correct, I think I did, but if I did it correct, then I got negative 2.68 for my notes. So hopefully that's right. We'll see. Okay, so I get negative 2.68, so that means I'm now ready to almost finish the problem. And let's come right down the rest of our problem. So once we know our z value, we're ready to find our p-value. And to find our p-value, I draw myself the normal distribution that I always do. Negative 2.68 comes on here. We are doing less than, and since we're doing less than, that means I'm going to shade that part of my thing, and so p is going to be that value here. Since we're dealing with a z problem, I'm going to use normal CDF because z is the normal distribution. So I'll do normal CDF. My lower will be like negative some really big number, negative 99999. My upper will be that negative 2.68. And make sure to leave mu as 0 and sigma as 1 because we always use the standard normal distribution when we do this problem. And when you do this, you get p equals 0.003. And so that's your p-value. Now all that's left is to come to a conclusion. We're comparing this to 0.05, so notice p is a lot smaller than alpha. P is a lot smaller than our 0.05, so that means we reject H naught. What does this mean practically? Practically, this means there is evidence that the second chemical is slower. Or is slower. So there's statistical evidence that the second chemical takes longer to react than the first chemical. Okay, again, this part right here looks the exact same as we've been doing all along. And this part right here looks pretty similar to what we've been doing. We just had to change the formula. And so once we change the formula, everything else makes sense. Okay, so now let's do the same problem, but let's talk about what to do when we do a hypothesis, or when we do a confidence interval. And so our confidence interval, well, our old confidence interval looked something like this. And by the way, this problem is a little bit manufactured because we know that it doesn't make sense to know what the sigmas are. But let's go ahead and go with it because it'll make life go a little bit easier. So here was our old confidence interval. So what's our new formula going to look like? Well, you might be able to guess what's going on. Instead of putting x bar, what are we going to put? We're going to put x1 bar minus x2 bar. So that's what we're going to have right here. And then we'll still have the ZC. And instead of the sigma over square root of n, we're going to have that real messy thing that we had earlier. So we'll have the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And this is less than, and now instead of mu, we'll have mu1 minus mu2. And so you can kind of see that our formula is going to look the exact same as what we had earlier. And here, tell you what, let's get a second piece and just keep writing over here to the side. And let's see how far we can keep writing. And this is less than x1 bar minus x2 bar plus zc times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And my guess is that you can't read that, but there it is if we kind of keep going. So the formula keeps going kind of exactly as you would expect it. This whole piece, instead of having a minus sign, has a plus sign over here. Okay, so there's our new formula. So all we have to do now is tackle this problem. If I want to create my confidence interval, all I have to do now is tackle that problem as I had just with my new formula. So that means instead of x1 bar minus x2 bar, instead of x1 bar minus x2 bar, what I'm going to write is I'm going to do 16 minus 21 times, or 16 minus 21. And then we'll go minus. Make sure to use parentheses here just so you don't get yourself too messed up. I don't think it'll make a huge difference, but you could potentially mess yourself up depending on the order in which you want to type things in your calculator. And then we'll go minus ZC times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2 is less than mu1 minus mu2 is less than ... Okay, let's not even write down that right-hand side. Now, I do have to figure out one thing. I do have to figure out ZC. Well, we've done this a lot of times, but let's remember what ZC is. We have a 90% confidence interval, so that means I want to have a normal distribution where this value is my ZC, and I have 90% in the middle. We've done this a bunch, but this side over here now has to be 5%, so I'm going to use inverse norm, and I'm going to use 0.95 for my area. And then I'll use mu equal to 0 and sigma equal to 1. So we're going to do 95% because your calculator isn't smart enough to know to stop right there, so you have to tell it 95% for the whole region. When you do this, you get 1.64 out from your problem. So you get 1.64. Okay, so ZC is 1.64, so let's type that in or write that in. 1.64, and then we have the square root, and we have to put all of our numbers in. 1.5 squared over 13 plus 4.8 squared over 7. And this is less than mu1 minus mu2, which is less than, and now I have to write the whole thing again with a plus sign. So what if I just come down to the next layer and write it down on the next layer, and then I'll have 16 minus 21 plus 1.64 times the square root of 1.5 squared over 13 plus 4.8 squared over 7. The only place that changes from plus to minus is in the only place that changes from plus to minus is this gap between your averages and your standard deviation part. So kind of your error term and your point estimate. So that's the only sign that changes. The other minuses stay and the other pluses stay, but that one spot changes. Okay, so let's calculate all this out. When I did it, I simplified. I typed those first two, and then I put all this in my calculator, and I got 3.05 for it. Less than mu1 minus mu2 is less than -5 plus 3.05, and so that means I got -8.05 is less than mu1 minus mu2 is less than -1.95. So that's what I got for my confidence interval. I actually want to take just a minute and compare the last two answers that I had together so we can kind of see something interesting that happened. So when we did our confidence interval, what did I get? I got a range that went from -8.05 to -1.95. And so this is where I'm 90% confident that my values are. So I'm 90% sure that the actual, not the average, but the difference between the two averages is somewhere between there. So I'm 90% confident that mu2 is between 2 to 8 seconds larger than mu1. So let's think about our hypothesis test. Hypothesis test, I'm asking could mu1 equal mu2? Notice this is the exact same thing, and some people even write it this way. This is the exact same thing as saying mu1 minus mu2 is equal to 0, right? Because if you just move the mu2 to the other side of the equal sign. So we're saying could mu1 minus mu2 equal 0? Well, where is 0 on this confidence interval? 0 is way over here. 0 is right here. Now notice, what does that mean logically? If I ask could mu1 equal mu2 equals 0, could mu1 minus mu2 equal 0, the answer is not very likely, because our confidence interval says most of the values are right here. So I want to make, so what was our conclusion with our hypothesis test? Our conclusion with our hypothesis test was that we rejected h naught. So we rejected this assumption that 0 was inside of here. And so you can kind of see that the two should go together. That when 0 is inside the confidence interval, you should end up failing to reject because h naught is a very reasonable result. When 0 is outside of our confidence interval, we end up rejecting h naught because h naught is no longer a reasonable result. The reasonable answers are the ones inside the confidence interval. So this kind of lets us connect. So we see that really, when we do confidence intervals and hypothesis tests, we're really kind of studying the same thing. We're just looking at it kind of through a slightly different lens or from a slightly different perspective. But the two tests should always complement each other when we go through them. Okay, let's flip the page in your notes. I'm now on page 53 on your notes. And let's ask ourselves, what do we do? What do we do when we don't know sigma 1 and sigma 2, and instead we have to use S1 and S2? And the answer is everything looks almost exactly like we did before. So what's going to happen here? Our H naught is going to be that mu1 is equal to mu2, and our H1 is that mu1 is either greater than, less than, or not equal to mu2, depending on the problem. So what you see is that our hypotheses are the same, whether you know the standard deviation or whether you don't know the standard deviation. But now, earlier, we used a t statistic whenever we didn't know the standard deviation. And we're going to do the same thing here. We're going to use t, and we're going to take that formula we had just a moment ago, except instead of using, so we'll do, here, let me just write the formula down. I'm having trouble talking and writing at the same time. So what you'll find is that our formula is in fact the exact same formula we had a second ago, except what did we do? We changed the sigmas to the s's, and we changed our z to our t. So this is the exact same thing that happened in the previous problems, where all of the problem falls out the same, and we use, except we change our sigmas to our s's and z to a t. Now, there's only one question, and that is when we do our confidence interval, we have to ask what are the new degrees of freedom. And there's a really complicated way to do the degrees of freedom, but what we're going to do is a simple way. We're going to take the minimum of our degrees of freedom here. Let me just erase here so we can see a little bit easier. We're going to take the minimum let me remind you that these are not professional. These are just like I would have messed up in class. So our degrees of freedom are now the minimum of whatever our n1 and our n2 values. So pick whichever one's smaller. If n1 is smaller, use it. If n2 is smaller, use it. So use the smaller of the two samples and then subtract 1 from it. So that's what we're going to use for our degrees of freedom. This is actually a really safe bet for degrees of freedom. There's a much better way we could calculate the degrees of freedom, but we're not going to use that. We're just going to go with the minimum of n1 minus n2. And that's going to work great for us. And then finding the p-value, we use TCDF. We use TCDF, and then we reject or don't reject depending on the p-value. So the big difference is this formula, and we just change our degrees of freedom ever so slightly. Okay, let's do that problem and see how much success we can have in it. All right, so let's come over here. A teacher has 2 sections of the same course. He gives a test to each of them. Let's do a hypothesis test. So we'll have 10.3 part A, and then we'll see how it's going. So what are our hypothesis? Our null hypothesis is that the 2 tests are performing the same. Teacher has 2 sections, and they want to know is one section different? Was one section different than the other? And then our H1 is going to be whether or not they're different. So we're just going to do a not equal sign instead of an equal sign. So H naught, mu1 is equal to mu2. H1 mu1 is not equal to mu2. Notice the teacher has no inclination of whether one should be better or not. They just want to say, are they the same or are they different? Okay, so now we go to our formula. And our formula, oh, it was not a z, it was t. T equals x1 bar minus x2 bar divided by the square root of S1 squared over N1 plus S2 squared over N2. And now we just plug everything in. And so we read our problem and everything's kind of showing up nice and pretty for us. X1 bar is the average on the first test, which is 73. X2 bar is the average on the second test, which was a 71. And then we square root those. The standard deviation on the first test was 5.5. And the first test had 16 students. And then the second test had 4.8 and 12 students. And so we put those in our calculator, and if I calculated it correctly, I got 1.024 for my total. Okay. So 1.024 is what I got for my t. And so now that I have that, I'm ready to go start calculating my p-value. So for my p-value, I take this probability, let's put 1.024. Notice it's a not equal sign, so I actually need to put two tails on it, a right tail and a left tail. What I'm going to do is I'm just going to calculate one of them and then double the value. So to calculate this value, I'm going to do TCDF, and we'll have our lower will be 1.024, and our upper will be whatever really big number you prefer. And then for degrees of freedom, we have to ask, well, what's our smaller of our two numbers? And the smaller of the two numbers is 12, and we'll subtract 1 from that and make it 11. So degrees of freedom will be 11. So we plug all this in, and we get for our answer, we get out for our answer 1.164. So our p-value has to be double that because this is a two-tailed test. And so our p-value is 0.164 times 2. And so our p-value is 0.328. Now, time for our conclusion. So our conclusion, how does p compare to alpha? Well, there's really no case in which we would reject a p-value of 32%. P is much bigger than alpha, so we fail to reject H0. What does this mean practically? I'm not going to write it down because I'm feeling lazy for the moment, but practically this means that there's no evidence that these two classes are performing differently, that the teacher has no indication there's any difference between the two sections. And by the way, this shouldn't be a big surprise. Notice one class scored a 71 and the other class scored 73. So it's not like they did that differently between the two tests. They were both kind of in the same ballpark. All right. Let's tackle the confidence intervals. And so now how do I want to do a confidence interval? Before we had this calculus, this confidence interval formula. You all are smart. You all are playing along at home. You know exactly how I'm going to modify this formula to fit what we're doing right now. Instead of x bar, x1 bar minus x2 bar. TC stays the same. And instead of sigma over square root of n, we have the sigma of s1 squared over n1. Oh, these should have been s's. I wrote the wrong formula. S1, instead of s over square root of n, we're going to go the square root of s1 squared plus s2 squared over n2. So you see we've got that same kind of standard deviation term, which is taking place of our standard deviation term. mu1 minus mu2, and then we'll have the same thing. Let's write it right down here. x1 bar minus x2 bar plus tc times the square root of s1 squared plus s2 squared. Oh, I'm failing. S1 squared over N1 plus S2 squared over N2. All right, so let's come and let's tackle what we're gonna do now for 10.3 part B. If you're feeling on top of things, I hope that you're working ahead of me and checking that this is going well. This might be a good place to pause and get your answer and see if you get the same thing as me. If not, we'll just keep rolling with it. So I'm just going to take this formula and plug in the values that I see. They're the same values we used a second ago. So it'll be 73 minus 71, minus. I do have to take a second to figure out what TC is. What is TC? Well, to figure out TC, I'm going to draw my picture. I'm going to put 90% in here. I know that I have 5% over here, and this is my TC value. So I'm going to use the inverse T button, and I'm going to use my area is going to be 0.95, and then my degrees of freedom, I'm going to use the same degrees of freedom I had a second ago, pick the smaller of the in values and subtract 1. So 11 will be my degrees of freedom, and this spits out 1.79 for my TC value. Okay. So 1.79 is what I get, and I'm able to plug that in and keep going. And then we've got the square root of 5.5 squared over 16 plus 4.8 squared over 12 is less than mu1 minus mu2 is less than, and then I'm going to make myself a little bit more space. The exact same thing with a plus sign in it. So sorry that I have to write it all again. I guess I don't have to, but I'm going to. So this with a minus and this with a plus. We calculate all of this. What if I just jump straight to the answer? Negative 1.49 is less than mu is less than 5.49. Let's compare the two answers and notice that where if I were to think of this is a confidence interval, I have negative 1.49 here and 5.49 here. Where does 0 fall in the confidence interval? 0 falls kind of somewhere right in the middle of the confidence interval. Let's compare that to the last problem. Did we reject or fail to reject? We failed to reject because the difference, mu1 minus u2 equals 0. That's a reasonable thing. It's right in the middle of the confidence interval. So you can see how the two, again, are connected to each other. All right. There is one other way we could do the degrees of freedom. If you wanted, we could use what's called Satterthwaite's formula for degrees of freedom. We could use Satterthwaite's formula for the degrees of freedom. And if you want, you can look on page 53 at the bottom, and you will see just how awful that formula is. If you were to do that on this problem, you would get your degrees of freedom to equal 25.32. So Satterthwaite's formula would tell you that the degrees of freedom for this problem should be 25.32, and you would get slightly different answers. So this TC would be a slightly different value when you calculated it out. And similarly, that p-value when you did it earlier. Actually, from part A, the old p-value was 0.328, and if you use Satterthwaite's formula, it would be 0.314. So what you can see is the Satterthwaite's formula made it a little bit smaller, but not crazy smaller. And if you do part B, the old formula gave us negative 1.49 is less than mu1 minus mu2 is less than 5.49. Satterthwaite's formula would give you negative 1.33 and 5.33. So you see the confidence interval got a little bit smaller using this formula, and our p-value got a little bit smaller using this formula. I don't think it got small enough to worry about. I think that for all of our purposes, we can just ignore Satterthwaite's formula and do it just like we did in class. So you don't need to be using that formula. But, quick note, your calculator has commands just like it had the shortcut commands to do your z interval and t interval and z-test and t-test. Your calculator has shortcut commands for these as well. And if you go look at the stats menu and go to tests, you'll see that we have the 2 sample z and 2 sample t, so 3 and 4 here. I don't know what number they are on your calculator, but 3 and 4 are two sample. So you can guess two sample z-test. That's a hypothesis test, just like we did on the first problem today. A two sample t-test would be a hypothesis test, just like this part A that we did right here. And then if you keep scrolling down, you'll see a two sample interval, which was for me is number 9. And if you look at the two sample interval, then that's an interval just like we did on the first part. And a two sample t interval is a confidence interval just like we did right here. So if you use those on your calculator, then your calculator will use Satterthwaite's formula. So you'll get slightly different answers from a calculator when you do it by hand, but they'll be very close. So don't let that concern you. Okay, that's it for 10.2, and that actually finishes all the information for the next quiz. So expect in the next few days for me to write out your next quiz. Is going to be a take-home quiz, and it'll have some problems where you get to do some confidence intervals and get to do some hypothesis tests on your own. And we will just do that, either scan it or take a picture and turn it in, and we'll grade those. So thank you very much. Good luck studying, and please come see me anytime you have questions, because I want you all to be super prepared for this quiz. Thanks.